I'm Ed Goddard with a group here in the room, and I'm pleased to talk to you about the GRAIL mission and give you an overview of where we are in the analysis of the data. Yeah, GRAIL was launched a few years ago now, not many years actually, but a few years ago, and in fact the data acquisition stage is now over. It ended in fact last December the 17th, 2012, and this first chart that you should be looking at right now just gives you a quick look of what the mission actually was. We had two spacecraft, essentially identical spacecraft, and the primary measurement that was being made by these two spacecraft was something, it was the link between the two spacecraft called the Ka band, if you can read it on the screen there. Now, that Ka band happens to be a very precise measurement of the distance between the spacecraft, and there's one measurement going in one direction and one going in the other direction, from which we actually can derive the range rate, and you get the range rate to the acceleration, etc., till eventually you get the gravitational acceleration. And so this is the method. The X-band and S-band are ways of sending data back, of making sure that we've got the timing correct on the two spacecraft, and that we can relate the measurements appropriately. But this is how it's done, and it is the analysis principally of the Ka band data that provides us the gravity field information, although it's true also that the X-band and the S-band are important at certain components of the particularly long wave aspect of the gravity field. Okay, on the next chart is just a picture of the interior of the moon, which kind of motivates us at some level to look at to study the interior of the moon. In fact, GRAIL has a prime mission science set of objectives and some extended mission objectives, which I will briefly cover in a moment. And I think if the next chart works properly, since it's an overview, yes, okay. The original prime, let's see if I can do this again. Yeah, prime mission objectives had this rather broad statement from crust to core, and it is true that we did and are trying to contribute through gravity to our understanding of the interior of the moon, from the core right to the actual crust of the moon. And this is enabled in essence by this Ka band capability and from an altitude above the surface, which to all intents and purposes was quite low, at an average of about 50 kilometers to start with. During the prime mission was lowered to about 23 kilometers, and eventually was lowered down to about 12 kilometers, another factor of 2. And I will come to some aspects of that particular work. If I move on, okay, yeah, in this chart as it's now annotated with the light blue color there, this is to show that the extended mission, we decided to exclusively look for the signals, gravitational signals in the outer layer of the crust, the top 10, 20, 30 kilometers or thereabouts. It's not to say that we were not sensitive to the gravitational attraction from the rest of the moon, but largely that would be, we believe, we began to understood during the prime mission. In fact, we could not have done the extended mission without having first done the primary mission and got a handle on the broad picture of the gravity field of the moon, and so that we can eventually look at the very fine structure that we can get, we believe we're getting in the extended mission. This chart here is really a table of how we set up the original objectives for the prime mission. And when we started out, we only anticipated having a prime mission. We thought the spacecraft would run out of fuel, they would eventually crash on the surface after approximately 3 months of observations, and everything was planned around that expectation. During that time, we set up, or for that time, we set up 6 primary objectives involving the crust, the thermal evolution, impact basins, magnetism, and the deep interior, and then inner core detection. And in some ways they get more complicated and more difficult as you move down the list from 1 to 6. And on the right-hand side, that right-hand column shows you the requirement that we set ourselves to contribute to that that particular problem of the crust. And in fact, we have met all those measurement requirements. That was achieved actually a little earlier on than we anticipated, but we did meet all the measurement requirements. Now, that's not to say that we've done all the science, because we formulated the initial science objectives in terms of actually getting to a certain quality of measurement. Frankly, we did not know what we would expect to find at these very short wavelengths. And so this was the first part of the mission. In fact, in some ways was the initial part that was enabled the rest of it in some ways. And the next chart actually shows this issue of the altitude of the spacecraft. If you want to see a size on the surface of, I don't know, 10 kilometers, then you really shouldn't be much more than 20 kilometers above the surface or something of that kind. There is a relationship that one can essentially develop. But to see numbers, and we originally said scales of 1 degree, which is 30 kilometers on the moon, we really had to be down at 50 kilometers, and that's where we set the original mission. However, no orbits are perfectly circular, and on the left-hand side in the red color there, you can see when we started out, our periaps altitude was about 25, went down to about 20, but the apoapsis was about 80, or 90 in fact, and as a function of time, they got closer together, and then they separated again, and this was planned to be this way. So we had a range of altitudes, and on the right-hand side over there, that minimum altitude variation during this period is in fact shown, where the blue says that, you know, we were down in some places because the lowest point was moving. It gets down to 20, 25 kilometers, 30 kilometers typically maybe, and one or two places where it's higher, particularly at the poles in this case. Okay, so if I can move on. Yep, next chart. Okay. Now, when we went to the extended mission, which we did not expect to have, we realized that with the fuel remaining, we could come down to a lower altitude, and we came down to about 23 kilometers average altitude. Of course, it varied somewhat, but it was in that range. And we set ourselves a whole new set of science objectives. And those are shown in this top chart here, which in the red and kind of purple on the far right-hand side, that horizontal scale, by the way, is from 10 on the right until you get to the end of the purple part there, which is extreme right, which is 30 kilometers. So we were looking between 10 and 30 kilometers were the objectives for this particular mission. And to get gravity information on a very high precision level for that range of sizes on the surface of the moon. And the 6 investigations that we established for the extended mission were structure of impact craters, near-surface magnetism, mechanisms of timing and deformation, causes of crustal magnetization, and estimation of upper crustal density, mass bounds on polar volatiles. Now, what we're doing right now is, in fact, we're trying to meet the scale on the right-hand side of that green right-hand green column, which says we need to get down to a few thousandths of a milligal, which is a very small number, for the acceleration of gravity, as seen by the spacecraft, to get these resolutions down, as we put it down here, to about 12 kilometers. And that's what we're doing right now. Actually, we're spending a lot of time in developing the models that represent the gravitational field of the moon down at these resolutions. And in fact, this is presenting some level of difficulty because the computational requirements are much more excessive than we originally planned. And in fact, we're going to be taking a little longer over it than we originally thought. However, all the data for this whole mission from beginning to end is now on the planetary data system. It is the range rate data and the Doppler tracking data from the Earth to the Moon, etc. Everything is there, but it's not the most convenient form that most people would want. And the gravity models from the Prime mission are now being deposited in the PDS for people to use. And I think if you go there now, you will be able to extract the gravitational field models that we have developed so far. That's only about halfway through the process. The tough work is coming on the extended mission, which we're in the middle of right now. Okay, the next chart just shows that variation in altitude during the extended mission. The top curve is the apoapsis altitude. It's a double curve. We have now to put in here the altitude with respect to a sphere, which is the kind of thing one would normally deal with when we're at great altitudes. But we also had to put in the altitude above the topography, because ultimately that's what we needed to stay clear of. And our rules were don't put the spacecraft in jeopardy for this 3 months period. Stay 2 kilometers above the highest peak on the planet. And the lower curve in the yellowish color, or curves I should say, show how we were on average around 15 to 20 kilometers. The average actually was, for the lowest point, was probably somewhat less than that. But when you see we get towards the end of November, when we've got our second 3 months taken care of, we had to plan an exit strategy, or an end game, if you like, and Maria decided we're going to chance our luck and we're going to lower the periaps down another factor of 2 until we get down to an average of about 10 to 12 kilometers. Now, you must remember, at 10 to 12 kilometers above the surface, you are also at the range of the dynamics in the topography of the moon. So we have 10, 12, 15 kilometers range of topography. We now have a spacecraft which is at that height above the mean surface, if you like, or any of these locations, and in some cases down at just a few kilometers. And eventually we ran out of fuel, we lost control of it, and the spacecraft crashed on the 17th of December. This just shows mapping again of during the altitude or during the extended mission. You can see the blue areas there are about 9 kilometers on the scale on the right-hand side there. There are a few up at patches up there at 27, and there are a few at about minus 90 right near Oriental, where we are down at under 6 kilometers. In fact, we're probably under 3 kilometers. We deliberately chose the last few orbits to be coming very, very low over the ring system of Oriental, and we were successful. And of course, these 2 spacecraft crashed just a few hours after that, those observations. And those observations are being processed right now, but they are, in fact, some of the most difficult. So this is what the KBRR of residuals look like. You know, we're talking about trying to make a measurement of velocity to, a few hundredths of a micron per second. Actually, that says meters to the minus 1. Actually, it's microns per second. Unfortunately, that got mistranslated here, but they're very, very small, accurate velocities, and it's from that we actually get the gravity field. Okay, so this chart just shows a picture of the gravity field of the moon out to degree and order 900. This is where we are right now. 2 groups, Goddard and JPL, are actively analyze these data to get to the maximum resolution we can get on the surface in global spherical harmonics. And right now that's degree and order 900. We expect to get to a little over 1,000, but there we think we'll have to go into local analyses of the regions, which will be done also at other resolutions as well. But we think we can get down to probably about 5 kilometers in resolution, maybe a little smaller in the global mode. And it will depend on where you are on the planet also, because of the altitude will vary. But the other point to remember is that it's not just the gravity. The next chart shows the topography. And of course, we have very good topography. So although the gravity field goes out to 900, the spherical harmonics for the topography goes out to about 2,500, maybe more. But that's sort of plenty enough. However, in the latter part of the mission, we were so close to the surface that the topography and the removal of the topography as an influence on the gravity field becomes more complicated. Let me put it that way. Okay, but when we do remove the topography, we get something called the Bouguer anomaly, which is shown on this chart here. And this is really the interesting stuff. Now, this is a high bandpass filter. We've removed the long wavelength shape of the body, etc. This is what we mean by degree 6L. That's a degree from 6 to 384. And this is the anomalous field that we're trying to explain and what we're very interested in. We've now removed the topography. Underneath this map, you can see actually the topographic black and white shaded relief to give you some feel for what's going on. But it's the colors that are the gravity anomalies of the Bouguer. And it is this interpretation which helps us to understand the interior of the moon. But this is a fraction of the gravity signal that we actually saw originally. And I want to show you that by showing what the coherence between gravity and topography is like. And this is shown on this next chart here, where the green line at the top goes up there to about 1, stays about 1, drops down at about a number of about degree and order 600 and falls right off. The importance about this chart is what I want to show you is that if you look at the yellow curve on here, which is the state-of-the-art until a little while ago from the
David, 2 minutes.
mission.
2 minutes left.
Thank you.
Sorry, 2 minutes left.
And then you can see that the Kagura mission did not see the high coherence at about 98% as far as it was able to go. So any interpretation that we did of our earlier fields, all the fields that we did on resolutions of 100 kilometers or thereabouts, have this deficiency associated with not the right correction for topography. Next chart is shows you that Bouguer power spectrum. It shows how at around degree in order 540, the power starts to go up. Whether this is real or not is not clear at the present time. If it's real, it could be real because we are real in the sense that the assumptions that we made to derive the gravity field from topography and compare it with the actual observed topography were wrong. Bill talked earlier about the densities within the crust. We actually assumed, or Mark Wazorek assumed or derived some densities that went from essentially the surface to 5 kilometers down to about 30 kilometers with increasing density with depth. That's what he derived from the GRAIL data. That was used here, but it was done on a global scale. And we know the moon is not uniform horizontally everywhere. So we need to look into regional effects. And what's more, into this region here, we do have the issue that when you get very close to the surface, the mountains are closer to the spacecraft, and therefore you see stronger gravity signals and higher frequencies. In the valleys, where you're further away from the spacecraft, you don't have that same resolution. So the global resolution now, when done this way with circular harmonics, becomes less accurate. Finally, the front and the back are different as well. I don't have time to go into those now, but not surprising, the coherence is different. What also came out in this work, very, very interesting, in the early work, or in the work during the prime mission, was that we saw linear features in the gradients of the gravity field. So you take the gradient of the gravity field, and you see features in the gravity field, which we've never seen in anything else. In fact, this is shown on the left-hand side, where there's the gradient of the gravity field on the left-hand side in Bouguer, and on the right-hand side is the topography. This linear feature was not seen before, and there are many of these linear features, quite lengthy ones, that in fact has been put down in the papers in Science as a likely indication of the expansion of the moon in its very early times, before shall we say, the contraction began a little later. A very interesting result, which we would not have expected and did not expect until we got the resolution of the GRAIL data. And a couple of charts on, since I'm running out of time, on the gravity and the topography of the Nectaris and Tranquillitatis area, showing the remarkable detail in the Bouguer gravity. When you think about the Bouguer gravity, the quality of that, although that signal may be a few hundred milligauss, its quality is down at probably close to a tenth of a milligauss, or maybe even less. So the understanding of these gravity data will take some time, but they have within them the jewels of understanding what's happening on the surface of the moon. Finally, we are still looking at the interior. We do have love numbers, which we said we would get. We do have, and that's on this chart here, we do have the low degree gravity field, which is very much, it can be and will be very much indication of the structure of the deep interior and possible motions of the deep interior. And that is being looked at by Jim Williams now, and a paper is actually, if not in press, it's actually being submitted to JGR on that topic right now from the primary mission. This is the list of papers that have been in press or published and are under assessment right now. The bottom two ones are the very high resolution fields. Another one will be coming out shortly from Goddard and JPL. Remember, there are two teams working on this to make sure we get it right. This has come out a little differently than I expected. You probably can't read it. I am having difficulty on mine here, but it is really a summary of what, in fact, I've just said. And I think the last chart is actually a picture that I've stolen from Dave Page, who may actually be online here for all I know. It shows that, in fact, the GRAIL spacecraft did impact the moon a little after going on through the Oriental region, impacted at about 75 north. and this is a thermal image from Dave Page, and there are two little spots on the red area there which show where the GRAIL impacts occurred about a kilometer apart. Just about as expected. Dave did not see the thermal increase as we hoped he would, but LROC has found the craters of these two spacecraft. They're small, 5 meters, with strange patterns around them, but yes, they're on the surface of the moon, and we hope they are protected now. In fact, we call them the Sally Ride Memorial Site, and we hope that will be part of the protection process for this site. So thank you, Greg. I'm sorry I may have overdone my time, but I'm there.
That's okay. We enjoyed it. Thank you very much. Yeah. Wonderful talk. Just an incredible mission. Let's take time for one question. We have one from Chuck Wood. Why does the near side look smoother, as if there is less resolution than the far side?
Hang on a moment. I'm being helped on this. Are you looking at the Bouguer gravity or?
I think he's talking about the Bouguer gravity.
Depends on what Chuck's looking at.
Yeah, Bouguer.
Yep, the Bouguer. Yeah.
Mm-hmm. That one.
Okay, if you're looking at this one here, yes, it is. I mean, you've got a lot of the Mare area, for example, where the cratering is just different than you get on the far side, and it is this front side actually. And I don't have time to go into it now, that shows differently on the coherence. In other words, the gravity and the topography are not as coherent on this front side in this particular region there. As a result, it looks the way it does here. On the back side, nearly all the signals go away, and you're left with these rather smaller features. But on the front side, it does look actually smoother, I beg your pardon. But that is a little deceiving because of the size of the features that we're looking at. I don't know whether that helps you, Chuck.
All right. Well, thanks again, Dave. Really appreciate it. Great talk. We need to move on right now. I want to make a procedural point here, just in terms of chat questions. If you could move all but questions on the for the current presenter onto general chat, that'd be great. We'd appreciate that. Thank you. So thanks again, Dave. Great talk. And